So in this video we will study how to compute the sample size for the comparison of the survival rates in two different groups, and we will use two cases. So the first one, we will assume exponential survival. That remind that the hazard function, the probability, the instantaneous probability of failure or death or whatever, or the event happening, is constant over time. And then we will study a more general case that is called the log rank test, in which the hazard function can be arbitrary, but there is an assumption that the ratio between the hazards in both groups is constant. Okay, so let's start with the exponential survival. So let's say that we are testing two different kind of knee implants, and we wonder which of the two will have a longer mean life. So we are installing this kind of things, and then we wonder or we care about the mean life of each one of the implants. How many patients do we need to study in each one of the groups to reject the hypothesis that both have the same expected life, that is about 8 years, with a confidence level of 95% and a statistical power of 80%, when one of them has a life that is at least 50% larger than the other? And we will assume exponential reliability. So we will assume that the probability, the instant probability of failing, is constant over time. So we want to show the alternative is that one has a longer life than the other one. The mu, remind, that is the mean survival time, and then the null will be the opposite. Okay, so for doing this we will use the statistic f, that is this ratio. It is our estimated mean life in both groups, and this is the way to calculate the mean life. So 1 divided the number of failures in the ith group, and then the sum of all the survival times. So for instance, if we have a fixed amount of time of observation, and a device has not failed up to, or an implant has not failed up to this time, then the observation time for that non-failing implant will be the observation time. So we have to sum over all the implants and the observation times, and if an implant is not failing, we will have the observation time, not the failing time, and then we have to divide by the number of failures, not the number of implants. Okay, and then this f is distributed under the null hypothesis with 2r1 and 2r2 degrees of freedom. So R1 and R2 are the number of failures in both groups. If all individuals are observed till failure, then the number of degrees of freedom is 2n. Okay, so it depends on whether we perform our experiment, we fix n up to some time, or we fix the time and then we calculate the n. Okay, so in our example, we are tracking both till all of them fail. So then we use the 2n number of degrees of freedom, and this ratio here, this is the ratio. One of them is longer than the other. This is the effect size, and then we have everything except n. So n is equal to 76. And maybe waiting for all these implants to fail, it may take too long. So we will stop the experiment when 90% of one of the two populations has failed. How many individuals do we need then? So let us denote as TF the time needed by the second population, the one with shorter mean life, to reach a survival of 10%. That is the complement of this 90. Okay, so then we can relate the survival rates in both groups. So we see that the survival in group 1 will be the survival in group 2 times this exponential. And under the null hypothesis, the expected number of failures is R1 equal to R2, because there, under the null hypothesis there is no difference. In the worst case, there is no difference between the both groups. And then it is this one. So the number of failures is n times the failure rate. And under the alternative, the number of failures in one of the groups is this one, and the second group is this one. So the equation for n is this one here. So we see that the number of failures here, now this is R1, this is R2, there is a mistake here. This should be R1 again. Okay. So yeah, so now we in our example, the survival in the group that decays more quickly, it is 10%. In the other group, it will be 19%, because the ratio between mu1 and mu2 is 1.5. And then again we have everything. So we have, so this 0.1948, it goes into the number of degrees of freedom. So this 1.61, this 1.8 are these things here. So it is 2 times n times this thing. And then we can solve for n. So we don't need to wait. So we can do the experiment in two ways. So either we take 76 implants in each one of the groups and we wait until all of them fail, or we can wait only until 90% of them have failed in one of the groups, and then we don't need to wait for the very end of the experiment. So for these implants that have a long mean life, or not mean life, a long life, it is not mean, the mean refers to the group, not to a specific implant. So we don't have to wait for the long lasting implants, but we have to increase the sample size. Okay, so the log rank test is very much used, and its assumption is that the ratio between the two hazards is constant. Okay, so let us say that we cannot assume a parametric distribution of this implant problem. So we cannot assume that the distribution is exponential, for instance, but we assume that the two hazards are arbitrary. So let us call H1, H2 the instantaneous hazard. So the instantaneous hazard is the instantaneous probability of the implant failing. Then we want to show that the hazard in one of the groups is larger than the hazard in the other group. So this one will be the one with smaller mean life. And the alternative, the null hypothesis, is the opposite. Okay, so given an instantaneous probability of failing, we can also compute the instantaneous survival function. So we will have S1, S2, we can compute the ratio of their logarithms. So the previous test on the hazards is the same as a test on this ratio. And then we want to show that the ratio of the survival times in one of the groups is larger than in the other. And the good thing about working with R is that we know how the logarithm of R is distributed. It's distributed in the when n is large. So this is called the asymptotic distribution. So the asymptotic distribution of the logarithm of r has this variance, in which we have 1 divided by the number of failures expected at a time tf, and this number of failures expected is n1 times this thing, and then for the other group is n2 times this thing, and then we can solve for the sample size n1 and 2 using the typical equations for Gaussian distributions. And Ra here in the equation is the log hazard ratio under the null alternative hypothesis. So it is the ratio between the two hazards and under the if the alternative is true, so it is kind of effect size. And if both groups are the same, and we make the two survival times to be approximately the same, then we can use this Schoenfeld's method. So this is just a simplification, because dealing with this equation is too difficult. So we can make the assumption that the survival time under the null hypothesis and the alternative hypothesis is the same, but this is not nonsense, and it is not nonsense, but it is not compatible with the fact that the null hypothesis and the alternative, they have different survival rates. But it is a way to simplify the equation, because otherwise this one is too complicated to solve. Okay, so then we have the typical sample size for Gaussian distribution. So we have the term on the confidence level, the term of statistical power, and then the normalized effect size. Okay, so Ra, that is this ratio between survival times. So in one of the groups, the survival time will be 20%, in the other group will be 10%, and then the ratio between the two is this 1.4. We have the logarithm of that, we have the sigma of the logarithm of r, and let us look at the formula again. So it is the number of failures that we expect in both groups. So sigma is equal to this thing, and then we can compute n. So n is just this. Okay, so we have to track 114 implants in both groups, and yeah, actually this is not sigma of log r. So this is the normalization term that we have here, because sigma log r contains the n. Okay, but it is related to sigma log r. Okay, so we have to track 114 patients in both groups. So 114 in one, 114 in the other. So we see that if we cannot assume a given distribution, the number of sample size is much larger. So if we can fix the distribution, we are putting into the system information, and then the number of samples is smaller. You see, from 76 we go up to 114. And that is another method, because okay, we have seen that this approximation has problems. So we have another approximated method, and then we don't need to assume that the survival after t at the observation time tf is the same in both groups, and then we can again calculate this sample size, assuming that So we don't need to assume that N1 and N2 are the same, but if we assume, then it is a very simple formula. In this case, so we have the same values as before. So let's say that the survival in the second group is 20%, in the first group is 20%, in the second is 10%. And then we have this ratio, and we calculate this thing that we needed for this is kind of the effect size, and then we need the normalization term, and again we need about 116. So we see that in this case both approximations give more or less the same sample size. So in general for survival analysis, we can say that what we compute is the number of observed failures that we need, and these depending on whether we are doing a confidence interval or one sample test. So we base our reasoning on the number of failures, and then we have to increase the sample size by the survival time at the end of the observation period. So this is what this equation is saying. So when we do the design, we say, okay, I want to see, or I need to see, I don't know, this many failures, and then I will increase the sample size. And most designs, except the log rank test, that is that can have arbitrary hazard functions, but there is the assumption that the ratio between the two is constant. Most of them, all these designs we have seen are based on the assumption of some parametric reliability model. So what is the survival time distribution? And we have seen three distributions. We have seen exponential, that has a constant hazard rate, so the instantaneous probability of observing the event is constant. And we have seen the Weibull, that the Weibull is the hazard ratio is very flexible. You can have more failures at the beginning and fewer at the end, or the opposite, or it can be constant. So it is rather flexible. And the last one we have seen is the normal, so a normally distributed time of failure. So the time to fail is distributed normally with some mean and some standard deviation. So this would be all for survival analysis and the sample size calculation for survival analysis. And see you in the next topic.